Welcome back, and welcome to our fourth keynote speech. This time it will be Dr. Khaldoon Naimi, who is from Nokia Bell Labs, Cambridge. I understand he's recently joined Nokia Bell Labs and getting to know people still, but he also brings with him a lot of experience. I'm just going to quickly read through the text that I received from Nokia Bell Labs. This keynote will be focused on advanced audio application empowered by signal processing and AI, with emphasis on hearing. And if I'm to be more specific, Nokia Bell Labs has a class of application called hearables, and it's one of the star examples of collaborative research. I think you'll talk a lot about that. Khaldoon is a senior research assistant at Nokia Bell Labs, Cambridge, and he finished his bachelor degree in 1996 in electronics, communications, and signal processing from Baghdad University, which is supposedly the most famous university in Iraq. He also obtained his MSc in digital communication systems from Loughborough University in the UK in 1997. And completed his PhD in advanced signal processing and coding techniques from the University of Surrey in 2002. He has, as I said, more than 20 years of industrial experience in algorithm development, signal processing, digital systems design, DSP, and so on. So one of my personal interests in this particular keynote is to learn how a powerful example or application such as hearable can potentially see future opportunities for settling machine or any machine learning algorithm for that matter. So please welcome Dr. Khaldoon Naimi.
Thank you very much for the invitation and for the lovely introduction. Today, I'm going to be talking about user personalized hearing experience through earbuds. Before I jump into the presentation, I'd like to open a question to the audience. What devices do the audience think we will be having in 2030?
I would sure they will be aware, not embedded.
Where mostly, yeah, or embedded. Or in other words, I mean, how many devices per person do you think we will have? I mean, if you think about currently, most people have earbuds or earphones, so that's one wearable. Most people have smartphones, smart wristwatches, so that's two. When they go jogging, they put a smart belt to detect, oh, that's three. But how many do you think we will have in 2030? How many? Very close.
Well, if you believe the fridge with a beer to be belong to a husband and
okay, now that's the link I haven't put, but you're very close. It's actually 15.
You might actually have some devices embedded in your clothing. All sorts of things.
Yeah.
Well, it's wearable on a wearable.
Yeah, it is sort of wearables. So they are actually predicting sort of 15 devices per person in 7 years, which is a lot. I mean, obviously, all these modalities and all these sensors have to be managed somehow. And they all have processing power. They all have batteries. So this is mainly the focus of what our group in Nokia Bell Labs, Cambridge. I come from the Nokia Bell Lab, Cambridge is split into various labs. I come from the pervasive lab. And the other term that we use is device lab, which is easiest, less of a mouthful to pronounce. And we mostly focus on the user is centric to the devices. And we try to make everything that happens or the interactions between user and devices to be seamless for the user, such that it's not a burden. So we look at augmentation, how the augmented aware cognition happens and how immersive communication happens. And we also look at three aspects, which is the form factor, the functionality, and the utility of the devices. And within that lab, we are sort of split into 4 groups. the form factor, which is really looking at the device itself, what processing power we need, the battery life that we expect, the memory, and how it looks, and how it's going to communicate. And the other group is the intelligence group, which really looks at more machine learning, federated machine learning, which is, I saw a presentation a while ago. And the system group really focuses on, you've got all these devices. How do you orchestrate the power of all of them such that if you have a very complex process, you obviously, if you rely on one, that will drain the battery, and then the others might be just sitting idle, whereas you can use them in an orchestrated fashion. And the last group is the user interface, or UX, where they really focus on the touch and feel of it. And over the years, we've had various successes. I mean, during COVID time, they came up with this Omni badge, which really has got a, huh? Yes, exactly. It's got an accelerometer, which is 9-axis, and it's got a microphone and air quality sensing. Basically, it was trying to tell you that you're coming too close. So this was a development that took maybe 6 months to turn around. And it was just because we were facing this problem and all the social distancing. So they had to come up with a solution, and that's what they came up with. And it worked, actually, in the building. When somebody comes closer, it alerts. And the other successes we have is the Omnibud, which is what Rashad has mentioned. And we have 2 generations of it, and I'll go in a bit more detail later. And we've got the OmniLens, which really is about, it's mainly adding a camera and IMU to the glasses. But what we wanted to see is that, can we predict people's deterioration of sight or illnesses? Because sometimes when somebody's having a heart attack, sometimes it shows in the face. So can we use a camera? Because we had forward-facing cameras, and we could have backward-facing cameras. So we were actually trying, in a way, we're suggesting that we can predict when your eye is starting to weaken, and for you to start, because these can be retrofitted, not on glasses, which are lenses, but on normal, non-prescription glasses, but they can sort of serve that aspect. And the last thing is Omni Camera, which is basically a surface camera where you can upload remotely some algorithm, which is a machine learning algorithm, to the camera to enhance its capability. And this was recently installed and tested in European, I think it's European Athletics Championship, where they had coverage of the whole stadium and the warm-up site. And you could actually say, I'm interested to see the warm-up. I want to see this runner on the warm-up. What is he doing? So you could actually, it's virtual on the phone. There is an app which logs into that. And if it doesn't have the software, it will upload that software and allow you to follow that athlete. So these are the few of the successes we've had over the years. So now I jump into my talk, which is importance of hearing. Hearing is a very important survival sense that we have. We use it heavily for communication between us. And we use it to tell when danger is coming, so directionality. So it's extremely important. But how do we hear? If I go, this is, by the way, it's not meant to be an anatomy lesson, so I will just go very quickly. The ultrasound, oh, how does this work? Press this button?
I wouldn't trust that.
Oh, okay.
It's not as smart as Nokia's.
The outer ear collects the sound surrounding the person and directs it towards the ear canal. The ear canal is a tube-like system which has a resonance in it, which means certain frequencies will be boosted. And up until the eardrum, everything is acoustic. When it hits the eardrum, that's vibrating, and therefore changing an acoustical energy into a mechanical energy, which then vibrates 3 of these little bones, which allow another boost to the signal, which ends up with a cochlear membrane. Now, the cochlear is as it looks, it's a snail-like system, which is full of hair, which is called outer hair cells, and these are submerged in liquid. So you can imagine if you've got a pump and you pull the pump, this vibrates, and therefore it resonates at the frequency which the ear canal is more sensitive to. Sorry, the cochlear. And the cochlear is not sensitive to all frequencies in all regions. It's split predominantly higher frequency. It's actually just high frequencies up to 20K at the beginning. And then if you go all the way around, at the end, it is sensitive to 20 hertz. So basically, if you open that tube, it's like a bandpass of filters. And every filter will show you, okay, this is now 2K, this is 3K, and then it gives you a signal. And this is just a show of high frequencies affect only the beginning, because it will still propagate, but they will not sense it. And when these submerged hairs move, they cause, when it moves in the resonance that is related to the frequency that it's exposed to, then transconduction happens and the brain knows about it. So this is the beauty of and it's a very small organ, not more than 30 millimeters, I think, and it's capable of doing wavelengths that is way beyond its size. So other fascinating things about the ear is that, I don't know whether you've seen this type of curves. It's called sensitivity curves or hearing curves, where if I want to hear a certain intensity over whole frequency, this tells me that I have to pipe a lot of power to hear the low frequency version of it. Then if I would have wanted to hear the 4Ks and all that, because that is more sensitive. So that means for the same intensity level in my head, I need to pipe a lot in the low frequencies and the very high frequencies, but very little in the band between 1 and 4K, because that's where our system has evolved, because it's very important for speech, that area. That's why it's actually very sensitive. Other interesting thing about the ear is because we've got 2 ears, obviously, so we sort of hear in a binaural fashion, and we can hear 3D. It's not 1D. It would be really bad if we just hear one plane. And what this is showing is that if the same sound hits me front on, or it's actually 45 degrees up or 45 degrees down, it has different shape when it goes in. And that is the outer ear sort of collecting the signals in a different way because of the angle incident to it. Now, think about that you've got 2 ears and a frequency here. So this is one aspect of it, which is an amplitude difference. There is another aspect, which is the time difference. So if you're moving in a plane like this, the ear knows that it's coming from there because it arrives left before the right. And it knows that the shape is different because this will be direct path, this will be shadowed by the head, and then arrive here. So this is all happening in the brain. And another fascinating thing is that most sounds that we know about, or the normal way of actually hearing, is that you think it's coming through the ear canal. But actually, the bone conduction, if signal processed properly, can give you a very good result as if it's coming through the ear, the normal conduction, the air conduction side of things. Now, another interesting thing is that I'm trying to show the effects of how the ear behaves naturally. So in this curve, I'm trying to show that in an open ear, which is the dark trace, there is a quarter wavelength. If you see the huge increase in the middle, when you just by the action of putting an earbud inside your ear, which is the light gray trace, that has disappeared. And then another one appeared in a double wavelength or half wavelength. And that is already causing unnaturalness for our hearing. So then we have to, as a signal processing, when you have this problem, you eventually have to compensate it by an EQ. Now, this EQ might work on Alex, but it won't work on Rashad because they have different ears. And that's where the user personalization comes into it. So all over the years, a lot of people have developed different types of headsets, some of that bone conduction, some of it over the ear, some of it sitting on the ear, some of it earbuds. Each one of them is designed with limited, you see, the design parameters are very difficult to satisfy everything. So if you want good hearing, or you want to protect your hearing, you obviously put a big one on your ears, make it massive, make it big mass, nothing will come in, but you will have horrible situation awareness. It will be heavy. It will cause you nausea because it's, weight on your neck. And you sometimes want to hear the pass-through. So if you don't have the situation awareness, you'll be like a deaf person on a very, and many incidences have happened in the HS2 where people were very well protected. They didn't hear a train coming past, and unfortunately it was a fatality of that. So it's one thing designing for one aspect, but to consider all aspects is a difficult thing. And then to personalize the design is a very hard topic. And this is just to show that wearables in general, I mean, the US are predicting something like 420 billion type of size of market. But the hearables or the earables, which is still a considerable size, which is increasing over the years, is going to be 80 billion in 2025 as a size of market. Now, when they design earbuds or headsets or anything, they actually don't quite pay a lot of attention on protecting the hearing. They just want to have a product that sounds good, and that's it. And when you go from underground, from one station to another, it's deafening. We did a study, not as part of Nokia, in a previous company, where we went through all the underground stations, through all the lines from one end to the other, with a what do you call it? A DBSPL measurement device, and we recorded everything. And it's actually, if you sit throughout the line, you're causing, and you do it daily, you're causing yourself a lot of harm, not knowing. But luckily, most journeys are like 2 or 3 stops and then they go out, which is fine. But if you had done this journey, like a train driver would definitely need a headset on top of his head. And I don't think anybody uses it. Anyway, so hearing loss is a big problem as well. And devices that deal with hearing loss are expensive. And they're non-portable. You have to go to a clinic and you have to test your ear. And there are various methods of doing that. You've got the audiometric test, which is the most known one. You've got what is called an OAE-based one, which really is used for infants. Because they can't react in a mechanical way. So what they do is they send a signal, and the cochlear is clever enough to send the feedback. So it's like when you throw a stone and the echo that comes back, that echo tells me how good your ear is. So that is what the OAE generally is what is used for infants, like I said, because they can't react. And when they go through a scan, and there is like a considerable worry over a certain frequency band, then they escalate it to a more specialist, then they come and look at it. So we want to do this again on a personalized level continuously. So that is our aim in our group. I mean, it's predicted that this is by the WHO organization that 1.5 billion people will suffer some sort of hearing loss in the near future. So why do we want, why is hearing personalization so important? It's important because, like I said, all our outer ear shapes are different. So how do we accommodate for all of that? And our ear canals have different widths and different shapes and different lengths, which all affect the resonances. And different sensitivity. So the cochlear between us, if we measure that, you will see that on yourself, you'd have not noticed that there is an imbalance between left and right. And that imbalance, if you think about it, if I'm deaf or not deaf, like insensitive to one frequency, and a dangerous car is coming within that frequency, it will skew me as if it's coming from there because I hear it stronger on my left, even though it's actually coming from my right. So that's where visual is very important in that aspect. You see, oh, okay, no, it's coming from me. And lastly is people have different preferences. So while we'll try to normalize the headset such that it is suitable for user X, we still give them the flexibility to change it to what they like to hear, even though it's out of our, we try to remember that setting, the user, and then we link it to a situation. So every time that situation happens again, we bring up that setting that they wanted. So personalization, I will explain it in part. So outer personalization is more related to when you occlude the outer ear using a circumaural headset or a on-the-ear headset, where it's actually occluding the whole ear and you can't get what is called the head-related transfer functions, which hold all the information related to elevation and related to direction and of the sources. Then I will give an example of how we try to sort it out in the middle ear. And where most of our interest is in the back end, which is the inner ear, because there's a lot of players already doing the front and the middle. But we think the missing jigsaw is in the back end, because not much work is done. Very little is known about it. So to solve the outer ear problem, because now I've occluded my ear, I need to somehow reintroduce the angle of incidence and the information. If you remember that, because of this simple elevation, the ear is receiving different amplitude variations based on the angle of shape and different delay as well. So I have to capture all that, and I create a database of what's called head-related transfer functions. And then I have to detect direction and then choose that HRTF and play it on both ears. It will bring that signature back, which tells me, okay, I brought it back. So this goes around in 360s, and many people don't bother about below the chin, because by then it's already distorted too much, and then you start adding more parameters. And to sort it out, the most compelling example of 3D reconstruction is if you think about a ring of microphones surrounding your outer, the headset, and each one is linked to an HRTF and linked to a speaker, which then reproduces like waveform synthesis into your ear. And it's as close production as if the headset is not there. So that's costly. as you can expect, because using many microphones, many HRTFs, and many speakers. And obviously size is a limitation as well. So many people remove the many speaker aspect and try to do it with many microphones, then mixed, artificially mixed, then speaker. It doesn't perform as well. And the worst, even worse, some people just do one microphone, which means for me, elevation will be a problem, and direction, like front and back, will be completely different. And I can't even get that back with just one microphone. So this is the worst case of trying to reproduce 3D. Now, the other part is what we try to do in the middle ear. So when you put, and this is mostly a problem in when you put earbuds, and if you remember, the movement of that quarter wavelength becomes a half wavelength. So to do this, obviously we need to characterize the ear when the user puts his earbud on. Some companies have already done that. And how it works, basically you've got a test signal playing through the speaker, and the microphone captures whatever is reflected from all around the ear canal, does loads of signal processing, and then produces a personalized equalizing curve that sits in front of any other signal that you are going to, from then onwards, pass to the ear. Like if you're listening to surround sound, that will then have the equalization here. If you're listening to music, because the earbud is fixed, so it's not going to change. Now, if you start moving and jumping around and jogging, this has to happen more frequently. So what we're looking at is that we don't want to send test signals all the time and disturb the user. We want to use the music he's using or the phone call he's using to regenerate the EQ in real time. And the last part, which is the inner ear. Inner ear is the hardest. And a normal, what's traditionally happens is that you go into a clinic and you sit and they place a headset on top of you, on top of your ears, and they play sounds. And when you start hearing it, you click a button, and that creates a curve. Now that curve sort of tells you your insensitivities, which obviously will deteriorate with time, will deteriorate with exposure. If you actually are working in a construction site or you're working in production of big machinery or military even. I've been in a military armored vehicle, and it's so loud that the person was beside me and I was shouting at the highest voice and he couldn't hear what I was saying. That is how loud it was. I mean, imagine them, most of them don't even wear headsets. They don't bother because they want, as soon as the armored vehicle stops, their argument is that I have to run with my gun. Yeah, but you're deaf, you can't hear. Anyway, they end up having a lot of trouble. So how do we sort out this with time? A crude way of doing it is that once you have this left-right sensitivity curve, then if I have an inner facing microphone inside the ear canal, I can then predict how much noise you've been listening to, and then using predictive analytics to then predict how much you're going to deteriorate if you keep on getting exposed. So let's say every time you rest the ear, it goes back. So if you have a function where you are predicting deterioration because you're under the exposure, but once you move into a silent place, there's also the ear recovers. I don't know if you've noticed, if you go into a nightclub in the teenage years, and you are standing beside the big speaker, that causes a moment in time, a window in time of deafness. You can't hear. Until you go to a quiet place, then the ear recovers. It's the similar concept. And the algorithm will follow the same approach, where if you keep on exposing, and there are a lot of these studies where if you stay exposed, for example, to 85 for more than 8 hours, then the employer himself is supposed to stop you from working and go to something else, which is quiet, so that the ear can recover. That rule doesn't generally follow in the military. But so a way of resolving it is that you've got the microphone listening to what the sound in the ear, because you're playing sound, there is sound outside creeping in. And then you use that with some predictive analytics to then predict that curve, because then if I predict the deterioration curve, I can predict how to present the information back to you in a more sensible way. Because if I have no idea of how much you've deteriorated, I have to send you to the audiometric clinic again. But this is a way of doing it online. But it's not the best way, in my opinion. So how do we do all this? My main focus is on earbuds, and this is our second generation earbud, where we need a lot of microphones. We've got two on the outside, and one on the inside facing into the ear canal, and a speaker, plus loads more of sensors. And we then have to come up with a list of algorithms that we want. For example, for the outer ear solution, we have HRTF. For speech enhancement, if something is coming as a speech communication from the other side and he's noisy, I have no clue of his noise, therefore I have to clean it up before I produce. Otherwise you won't hear it anyway. And I have to add the EQ into it such that I will make it sound the best that it can. So our system at the moment we've developed many of these algorithms internally, and we're waiting for the final sort of spin of the hardware to test all these algorithms. And I'd like to draw your attention to the algorithm control, which is maybe the only part which is machine learning in my presentation, where basically this algorithm controller, if you imagine you've got a number of enhancement options that you can add or subtract into your device. For example, ANC is one of them. If you want another one, which is you want to enhance comms, if you want to better situational awareness, if you want better protection, for example. You switch things in and out, but how do I switch it without having the user interaction? So basically, if you have the outer microphones listening to the environment and then changing that signal into, or feeding that signal into an MFCC block, which then into a machine learning block, which then triggers. So if, for example, you're walking on the street in London, you suddenly decide to go in the underground, the noise profile has changed, which then automatically triggers the user, not the user, the headset, to then say, oh, this is now dangerous. I'm going to switch on ANC. And I'm going to disable pass-through, because there's no point in having pass-through. You can't hear anything anyway. You switch on ANC, you protect the user further. So this is the machine learning aspect that I have worked on, but others in the group have worked on more complicated things. So the challenges we have is because we are using an earbud, obviously compute memory is limited. They are battery powered, and we are looking into batteryless or intermittent computing as well to do all these algorithms, because some of them don't really need an outcome instantaneously. But the ones that don't, we can actually switch them into this batteryless branch of signal processing rather than the real time. For example, ANC, you can't use intermittent because the noise has evolved and you can't really use it. But for things like the algorithm control system, you can actually shift it to intermittent computing and compute it a bit by bit until you reach a solution. And it's good because you don't want your headset to keep on switching things in and out very quickly. So to actually list our efforts, I think you're more aware of this eSense Earable, which is our first attempt at an earable computing. It's the seed of the field of earable computing, where the lab actually produced 1,000 pairs of these and distributed it to 70 research groups. And this was very basic because it only had one microphone, one accelerometer, and just could really transfer data to a phone where most of the clever processing is happening. Now, the second generation is much beefier. It has a microcontroller with hardware acceleration for AI, because now it seems like the trend is moving from downloading data to edge, but doing everything on the headset itself. So things like federated learning, and because it's actually battery operated, obviously we're looking at algorithms that are not that power hungry, just like settling machine.
Allowed to ask question?
Yeah.
Does it heat up when you wear it?
No, the thing is, the way you design is that you need to keep an inner outer ear canal block, not block, access.
Space.
Yeah.
Space.
And then you take that into account when you design ANC. So you purposely let the pass-through in, which is stops your ear, because when you block the ear, it starts sweating, it starts getting irritated, and it needs to breathe. So we sort of put that in the design of the mechanics. So this headset has a 9-axis, it has a PPG, it has a temperature sensor, 3 microphones, and we've already done a lot of IMU related things like gesture, physical activity detection, head movement, dietary. We know when you're eating. That's all through the ear. And we've gone a step further that we actually can. No.
Can you talk a little bit about the machine learning accelerator that you do?
It's a Maxim accelerator, Maxim 78,000, I think.
Yeah.
And then there is another generation which has more memory, I think 78,002.
Yeah.
It has, but it's limited to one type of, I think it's CNN. I don't work on that field, but I think it's CNN based. So, and you can do a lot of, what we're thinking is that depending on the model, for example, if we know he's active, we're trying to reuse the same hardware to then bring the model in, which is to do activity. And then when he's munching, we download another one type of thing. Or we're looking at the group that is looking into that is the intelligence group, where they're looking at maybe running this in the background. And if the chewing becomes more important, then it goes up and so on. So we're looking at what is the best way of using that very limited resource between so many algorithms that are contending. And one successful thing we've had is being able to actually measure the blood pressure and the heartbeat through the ear using both PPG and microphone. And now we're looking at respiration rate. We're looking at, if you remember the autoacoustic emission, we want to be able to measure that, to then map that to a sensitivity of the ear continuously. And that part will be a lot of machine learning when we reach to the data that we need. So to conclude, I gave a brief overview of our lab, an introduction to hearing. I hope it wasn't that boring. Various important parts of hearing and the problems using headsets, because headset design is a very careful balance, and I've yet to see a headset that satisfies all the designs. They cannot. And the various solutions we are trying to implement for personalization and continuous evolution of that. So if you, the headset has to be also intelligent, such that if it detects a weakness building up, it will compensate and it will alert. So it can be linked to a medical doctor, for example. And if it deteriorates too far, they might actually call you in for a hearing test. Or it might be an indication that something more sinister is happening, an illness, because that can be detected by the eardrum as well. So various things we're looking at from a health perspective. And we continue to trying to achieve the perfect user personalization in a continued and an adaptive manner. And that concludes my talk. Any questions?
Before anyone asks a question, can we have one of these prototypes for our lab?
Yeah, I'll pass the message to Fahim. Yeah, I think for the next generation is going to follow the same, the 1,000 units.
Yes.
We're aiming to do the same amount for this. That is, this being a bit more expensive, we might be a bit short than 1,000, but we will definitely aim.
Hopefully, I have one free and one we can buy. Any question?
It's the weight of a normal earbud. Yeah. No, that's
Put it on.
no.
Hello.
Yeah. So is there any direct communication between the left earbud and the right earbud?
The thing is, each one is designed independent of another, but you can share through Bluetooth because it's got the Bluetooth link that you can pass data across if you wanted.
Okay, so the next question.
That is actually, they all have their own DSP, their own microcontroller and everything. And they could easily just work independent. And that's the way it should be, because left and right might deteriorate in different rates. For example, if I'm looking at the hearing loss aspect of things.
But still, getting data of both the ears at the same time, so integrate will help better, right?
No, because I mean, we've got Bluetooth, which links to a phone, for example. The Bluetooth allows you to have a bridge between the two devices such that you can transfer data across, and this transfers it down.
Okay.
So it depends who's the master. It's either going that way down or that way down. And you could get audio and data, sensory data, which is the PPG, IMU. You can get all that, but the audio data would only work on the master side of Bluetooth, because that's the only part that will enable the mic. So you need to forcefully switch roles in your code, but you can still do it, but not at the same time.
Like you mentioned before that the processor is embedded in the edge device. So is there any work going on embedding the processor in the case of this microphone? Like for sure, if I am wearing not microphone of the earbud,
Yeah.
Like if I'm having a earbud, for sure I'll be having the case with me. So is there any work going on integrating the process in the earbud case?
The
So that-
earbud has processing power as well.
Okay.
The charging case has processing power as well. So we are doing that, and you can update programs on the air as you choose. You know, you're developing something, you can send one code to the other if you want to test two things at the same time. But you send one code to here, one code to here, and test two different setups. You can do it.
Thank you.
Yeah, hi. Thank you for the nice talk. Actually studied in Finland. Back in those days, Nokia used to make
Yes.
good mobile phones.
Yes.
And I'm not aware if you're going to actually produce them.
There is a desire to, yes, because I mean, I am part of the Bell Labs side of Nokia, and there is strong encouragement to spin off companies,
Right.
and to incubators. And the way it works is if you show potential and you show results and you show working demos, then they'll be more enthusiastic to support you.
Yeah.
And then basically just take the group, you go into a company.
Right. So it gave me a couple of thoughts from your talk. So first one was, I think currently I have a couple of earphones and headphones. And I think one problem I see, and probably you could also talk about, is that if you wear them for longer period, they also give you pain,
They
especially
do.
earphones.
Yeah. Because the pressure, they haven't balanced the pressure.
So I don't know if this physical design that you're showcasing, is there any?
Because yeah, there is a tuning leak between the outer and inner ear. We introduced that leak purposely such that it increases comfort.
Right.
Because if there is no leak, I mean, this is the thing when they design, they go seal it completely, make the best passive block, but then that's against comfort because you can't wear it for more than maybe half an hour.
Right. And second question is that you talked about battery and edge computing.
Yeah.
So I think we have this phenomena that, especially in automatic watches, that they can keep working because of the movement. And especially, for example, in my personal case, I use earphones or headphones while walking and listening to audiobooks. Is there also a possibility to charge them to some extent by walking?
We are looking at, they've already, this is before I arrived, they've already got energy harvesting work going on. But I think the mechanical one, where you move, doesn't produce much.
I think it would be even better to charge it while you're thinking.
What is it?
Even better to charge it while thinking.
Singing. Yeah.
Thinking.
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 Ah, yeah.
Thinking. It was a joke, sorry.
I mean, we're looking at, obviously, because we're limited in battery, we're looking at other aspects of how to charge it because, yeah, or conduction. The way we were sort of introducing to the military is that we wanted to, the military headset is big. The cable that goes down is very thick. It's like, because they try to isolate everything. Because think about the jamming. People are trying to jam your signal to make your soldiers, they don't know what's happening, and that's chaos. They want chaos. How to do it, how to protect against it, shield everything. So each wire is shielded, grounded to one end, grounded to the, but it's heavy. So we said, okay, can we have a ring here where only this is to a switch box, ring, and then some type of wireless. They said, no, anything conduction we don't want. So, but this could have been an easy way of giving battery. But they didn't. They don't like this. It's too insecure.
So, do we have any other questions?
Great talk. I assume that if you want to take this to market at next level, your closest competitor will be Apple.
Actually, yes.
Yes.
The problem with Apple is they have, obviously they have a massive monetary advantage.
Plus, yeah, they have your data as well, right? They are coming with AR, VR headset. They already have smartwatches, so they have already a lot of data on you.
They can't do the same as what we do in our headset.
So what will make it different, and what
we do all vital signs using the same headset. Whatever they do on the watch, we do it in the head.
But my understanding is that Apple might already be working on this, and
yeah, the thing is we have to spin up it quickly is the answer. Yes.
Yeah, and yeah, okay. Anyways, that was my question. Like, yeah, exactly. What?
I can take one last question, or maybe any comment. Okay, Alex.
Obviously, protecting people's hearing is maybe where you started with the device, but you seem to be collecting a lot of other data now about someone's lifestyle. I was wondering if you are in conversation with medical professionals in terms of what is the most important data to collect on that front.
Yeah, I mean, we have a project which is respiratory rate with NHS itself. And it's really based on this device, where we're trying, basically, when you go in and then, for example, if this is so cumbersome, and then when they breathe, they're going to breathe and it causes a lot of nausea when you, just to get the volume. But if we could do it in the ear and we could sort of maybe cut it down a bit and use it as a medical device, where it gives you blood pressure, heart rate, volume, oxygenating, and all that stuff. And one, you put it in, it's non-cumbersome for the user, and it will give you all that with reasonable accuracy. That would be another path.
Yeah, as long as it's accurate enough. That's always.
It's very. I mean, we've got I have a slide which shows accuracy is pretty similar to medical devices in terms of error.
Just augmenting Alex's question. When you put something on your body, there are various other things that you can sense. For example, heartbeat. Potentially, yeah. So,
we do it.
And sometimes also sensing things like wheezing sounds. From
yes, we do it.
Those kinds of things.
Yeah.
I've seen some demos from Siemens some time back. They were doing something similar with their,
we can detect. We're trying to also link it to. Basically, I mean, the main aim is to detect when you start developing Parkinson before you even do it.
Yeah.
Because that affects. The theory is that you start losing control. Too many things, and that shows signatures in either audio, blood pressure, or a combination. The problem is getting the test subjects to do it. So by the time you get to the test subject, is already gone. It's happened.
This is a common problem with multimodal data.
Yeah,
so you have too many data. You don't know which one to signify more than the other.
I mean, you can come up with measuring on us, but obviously we are hopefully healthy folk. It won't show anything, so you ignore that method. But maybe on somebody who's marginally going to develop, that method which you ruled out might actually work well. So it's very difficult when it comes to medical.
You might actually develop a relationship with the NHS, whereby you might actually develop a relationship with the NHS, whereby you actually offer this for free to the NHS to use on their potential patients.
But isn't there a lot of liability? I mean,
the legal side I'm leaving out of it.
You see, we think engineering wise, I don't mind doing that, but I think there's a liability if it if it's fails or causes a sound which really shouldn't be there. Because we're even we're even looking at predicting your state of mind and knowing that, okay, you're developing anger, let's calm you down. And from past experience, calming you down is playing ABBA to you, for example. Then we'll play ABBA in the background. On top of the music you're playing, we'll play you ABBA to the point that we calm you down. That's what we're trying to do, things like that. Obviously, the back end is all machine learning, but the front end is all acoustics.
Okay, come on, I'll give you the last one.
Yeah. So this is not exactly like a question, but I have something to say. Like following the question, what Dr. Jagmohanji asked. So I would like to say there's Sony also. They are also good in making headphones or earbuds. So there is one such earphones that I've been personally using it from past 4 years. I see they don't have a ML processor or something. They just have a noise cancellation technology inside the headphone. But they can do much more. Like they can have adaptive control. Like when let's say it can isolate the noise completely.
Yeah, that's.
But while you're in a traffic or any situation, it knows when to control itself. Like
yeah, I mean,
it reduces the sound. So when we have ML accelerators here, so what kind of what do you say? What kind of improvement that we can achieve? Having such kind
I
of
don't think the ML will help in that way. The ML will happen automatically controlling in a better way.
Maybe if we can integrate some kind of processing, like small processing, and even though we have like a overhead headphones, but even then having a small processing technique, we can achieve much farther. It can be.
I mean, in signal processing alone,
integrating it with the ML processor.
Coming from a non-machine learning background myself, I could solve most of this in signal processing, but to make it general to everybody and automatic, and it's difficult. You need something like a processing brain that bases it on your experiences, your preferences, the outdoor signatures, because I could easily just measure the outside microphone, the inside microphone. If I can't cancel it, I'll switch my INC off anyway. What's the point of doing something that I can't achieve? And that's why it doesn't need machine learning. You just integrate the two microphones over a 1 second window, you can make a decision. And that's how they do it. They might have a handful of ANC approaches, feedback being the least effective, going all the way to adaptive, which then covers the whole range. It's wider, but it's processing more. So you can actually switch things in and out, or have them, 3 of them running, and then switch one of them to the speaker or not, based on that control that you did. So you could easily do it without machine learning, which is what Sony possibly do. But because we do much more, yeah, we need machine learning.
Would there be an obstacle from introducing machine learning, because everybody thinks machine learning is too heavy because of neural networks and so much energy and efficiency? But if there was machine learning, which is
yeah, I think they've already had contribution in settling machine. That's before I arrived.
That's the consideration.
Yeah.
Okay. On your note, when you said Nokia is thinking of spinning out, some business model around it.
Off, yeah.
I know some people in this room who have some knowledge about that as well. So Fahim will be met by colleagues in this room as well. Great. Can we all thank Khaldoon and Naimi? Thank you very much. Thank you.